Can you hear me all right?
Yes.
Okay. And can you see the screen share?
Yeah, the screen share seems to be working. Are you ready?
Okay.
Let me just introduce you.
Yes.
Okay, so our next speaker will be Chiara, who will be telling us about Posetal diagrams. Go ahead.
Okay. Thank you so much to the organizers and to the scientific committee for giving me the opportunity to speak at this meeting. I'm very sorry not to be able to join you in person today. So what I want to speak about today is recent work I did in collaboration with Jamie Bickley, my supervisor, on string diagrams that have Posetal shapes. The content of this talk is in an archive paper with that number over there. So the context in which we're working here is that of higher category theory, which is a branch of mathematics, which offers a radical unifying perspective on vast parts of mathematics, physics, and computing. It's found applications in homotopy theory, topological quantum field theories, and reverting. But the main tricky thing about it is that actually working with higher structures in practice is not an easy task due to the burden of the coherence data. So one of the ways to address this is to work geometrically with diagrammatic methods to be able to reason with the structure. So the goal for today is to generalize cubical n-dimensional string diagrams to a Posetal variant which allows for really intricate branching structures. So I expect most of the ACT audience to be familiar with the idea of string diagrams. So this is certainly not a first introduction to the topic, but what string diagrams are in a single sentence is a geometric calculus, which is dual to the pasting diagrams we may be used to. And the basic mechanism for reasoning with string diagrams amounts to constructing homotopes geometrically, and these algebraically witness equivalences of n cells. We take a very computational perspective on string diagrams because these days there are a wide range of proof systems that use string diagrams for compositional reasoning in monoidal or higher categories. So the one project I have worked on myself with a long list of collaborators is homotopy.io, and yeah, there is a way to frame in the work that I'm going to be talking about as a continuation spiritually of the work that went into this proof assistant. So this works with higher dimensional semistrict higher categories entirely diagrammatically. Symmetry-free higher categories on a signature. And the reason why this is an interesting thing to consider in terms of mathematical statements that we can prove is sort of summarized in the following a bit mundane observation, but I would like to include it in my talk because it really distills a lot of the essence of what is going on here, is that if we're logically minded and we take some kind of statement about some algebraic structure, let's say a group, something that we can do is we can trade away these quantifiers for generators in a signature. And then we can perform a computation in a free structure on the signature and verify that a certain statement holds, and then we can transport it across into other structures. And So the way this, for instance, works graphically is we start by assembling a signature with these kind of variables, and we compose things, which string diagrammatically means we just put them next to each other. And again, the main reasoning principle is to construct homotopes here. And we have a powerful primitive in this sort of proof assistant, which lets us contract down this expression into the identity. Since this allows us to produce a homotopy into the identity, we know that there is an equivalence there, which computes this mathematical fact. So the way making sense of what we mean by a higher dimensional string diagram is not an immediate thing, and this mostly comes down to the fact that in higher dimensions, the familiar story of the powerful coherence theorems we have for dimensions breaks down. So what I mean, what we normally mean by higher dimensional string diagrams in the setting is as formalized in the theory of associative n categories, which was introduced by Christoph Dorn in his PhD thesis. So these are a model of strictly associative and strictly unital higher categories. So all the weak structure comes from the interchange. And conjecturally, we believe they are able to model all fully weak higher categories. Now, what we will mean by higher dimensional string diagrams is sets in free associative n categories. And what is nice about this is that we have a combinatorial encoding for this in terms of a zigzag construction. So detailing it mathematically is a bit verbose, so I will stick with pictures. So if we have this string diagram here on the left, and we want to make sense of it combinatorially within this framework of associative n categories, we can start from a zero-dimensional picture, which is a bunch of points. And we use this zigzag construction to iteratively encode this in this framework. So one-dimensional zigzags are just a sequence of spans. They're really determined just by their length. But this form a category, and we can take zigzags of zigzags iteratively. So the next step, this is a two-dimensional iterate of this construction, which we can then assign labels to in accordance to the picture we have here on the left, which shows the string diagram. So we can assign the topic information, which follows the colors. And we obtain a combinatorial encoding of this picture. Now, something to observe here is that the indices of the spans are indexed by total orders, or rather, like by the number of them that we have in a given zigzag, which we can think of it as a totally ordered set with a set amount of elements. And it's really a total order because this comes into play in the definition of morphisms, which are then indexed by monoidal maps. So we generally have a forgetful functor which reads off the underlying total order of each zigzag. And this data can also be described in another way, which is if we look at that zigzag, we can look at the legs of the zigzag, and these are indexed by the by non-empty total orders. So if we're looking here at this thing on the right, there is a zigzag of length u, and we can read off the these two associated total orders that are there, and they determine each other. And the way we make sense of this way in which they determine each other in a way that is compatible with these monotone maps is that there is a duality there between the category of total orders and the category of non-empty, and the opposite category of non-empty total orders and first and last element preserving maps. So these two categories are dual. And I want to see what this project is about is that, so if we take this view that string diagrams here are indexed by like in this cubical shapes are indexed by total orders, we can then embed the total orders into finite posets, and if the duality extends along this embedding, then this is a really exciting possibility, because then we can try to follow this duality along the embedding and try to make sense of a theory of string diagrams, which is vastly more general and can emit really intricate branching behavior. Now, the crucial thing to get a proof assistant out of the theory of associative and categories, which is what happens in homotopy IO, is that we have a series of high-level procedures which allows us to construct really complex homotopies, which in our dictionary means really complex proofs within this proof assistant very easily, which is not something that we can give for granted, because here we're working in higher dimensions, and constructing proofs explicitly becomes really really hard really quickly. So the way this works at the level of the categorical abstractions is that we are using limit procedures which geometrically contract the diagrams we're working with. And the goal for today is to generalize the zigzag construction to a Posetal variant while still retaining these high-level methods. And the idea we have here is that this construction would yield a new notion of higher categories with a geometric essence, but that have a richer structure that we can explore. Now, the reason why this is not like an immediate straightforward task to do this generalization is that the second we give up on this assumption that everything is totally ordered, we have to be a bit more careful with the behavior of our duality. So the way we can think of this process of dualizing an order structure is by think of it as scanning through this order structure. So we think of the order structure as something that describes some events and some information on causality. So this has to happen before this other thing, or X and Y can happen independently, right? Here we're looking at a total order on the left and a discrete poset on the right with units. And we can think of it, we can think of the dual order structure associated to this as giving families of events which are causally compatible. So here on the left, we see that this line that I just drawn says that both A and B are yet to happen. And then maybe if we scan through it, then we have another line that says A has happened, but B still hasn't. Whereas on the right, the situation is much more complicated, because here we can describe a situation where Y has happened but X hasn't, or X has happened but Y hasn't happened. And then we have another line that scans through and says both events have happened. And we can see it also at the level of the seeing the same thing with taking these cuts that I've just drawn and trying to give an order structure about them. So redoing the same game of scanning through this poset to construct put an order structure on these families of events. And a remarkable fact about this process is that the kind of order structure that we get here on the right has always a really good set of structural properties, and in particular is a finite distributive lattice. And this algebraic fact goes under the name of the Birkhoff representation theorem. So the way we formalize this is that if we take a poset, we can home into the working arrow as a poset. And this gives us a home set, and we can put an pointwise order relation on this. So the cuts I was showing before really correspond to the elements of this home set. And this pointwise order relation makes this specific family of home sets become finite distributive lattices. And the other way around, we can take a finite distributive lattice and look at the home set that we get by homing into the working arrow, this time seen as a finite distributive lattice. And we get a functor back into finite posets, which gives the other functor participating in this equivalence of categories. Now, we can see this result as a finitized formalism duality, but the crucial fact here is that this is the way that the duality that we have seen before that really powers a lot of the beautiful combinatory properties of the zigzag construction generalizes to the set, right? So this is how this duality extends along the embedding of total orders into finite posets. Okay, so we have this way of making sense of this duality, but for the purposes of our diagrammatic calculus, this is missing something. And the reason why this is missing something is that if before we could identify the elements of the original total order with events in which, so we're talking about A is yet to happen or A has already happened, and the elements of the original total order would correspond to things like A is happening right now. Here it's a bit more complicated because yes, we have X is happening right now or Y is happening right now, but we could also have X and Y are happening at the same time. And so the order structure here becomes vastly more complicated, as already shown in this very minimal example. So we can introduce another algebraic gadget that can capture this behavior really well, and this is given by this notion of intervals. So here we define an interval in a finite distributive lattice to be a pair of elements of this lattice that obey that like are related by the order structure. So one is less than or equal to the other. So we put these square brackets around a lattice to say that we want to talk about the intervals, and there is a way to partially order this set by a sort of precision relation or reverse containment relation, which really looks categorically like a twisted arrow construction, right? And this may not be the thing you immediately think of if you want to have a general notion of an interval in a partially ordered structure, right? You may think of like the set of things that are bounded above and below by A and a prime. But the advantage of this definition is that whenever we have a monotone function, we can push forward the intervals by this monotone function, because it's going to respect order pairs. So let's look at an example. If we take the kind of lattice we were looking at before, the associated intervals on it is this beast of an object. Is a bit ugly to put on a slide, but it can make a bit more sense if we gray out these specific things here, which correspond to things we can describe in terms of certain purple squares, which we can characterize in a certain way, which I will not go into right now. And once we take this data and decide that we want to describe it in terms of universal properties, such as Popax, we can remove it from the picture and rearrange this into something that makes a bit more sense, or follows the order structure there a bit better. So here we start to see again how this is sort of generalizing the previous zigzag construction, which was in terms of sequences of spans, in terms of things that can really support really intricate branching structures. Now, if we're happy with these gadgets in place, then we can assemble them into something quite powerful. Because now we can take a finite distributive lattice, and we can take the intervals on it, and if we have a given category of labels that we have fixed, then we can take the category of functors from this category of labels, like from the intervals into it. And if we have a lattice homomorphism, we can map, we can act by precomposition by the corresponding map. And this defines a functor from the opposite of finite distributive lattices into the category of categories. And we can take a Gaussian construction on this, which means that we can assemble a category whose objects are a choice of a lattice, which gives the shape, and then a labeling in C out of the intervals in this. And similarly for the morphisms of this category, we can take lattice homomorphisms that change the shape, and then we can take a natural transformation which does the relabeling based on that. And the crucial thing here is that this category C can be whatever we want. So we can take C to be L of C, and we can iterate this construction, which is really important to get a combinatorial description of these objects in higher dimensions. And so this defines a nice category for us, which we understand really well. And we can then carve out Posetal diagrams as a full subcategory of this, where the objects, the label part of the functor into C preserves certain Popax, which we can characterize and correspond to the grayed out squares before. So to concretize this a bit into a picture, then we can take distributive lattice as a shape, and we can take the intervals on it, as we've seen before, discarding the ones that we make sense of in terms of Pompac squares. We know this is going to be preserved by this condition, and the way we make sense of the labels on the string diagram here on the right is with this following scheme. So really, for instance, the G on the left is the label we're assigning to AC. The H is the label we're assigning to the interval DE. and so on and so forth. And the crucial thing to really, really stress at this point is that this is a one-dimensional string diagram here, which has a branching structure. It's not a two-dimensional thing. So when we keep iterating this at every step of the way, we have immense flexibility in the intricate branching structure that this kind of objects can describe. Now, there is an advantage to having defined this via Gottonian construction, and that is that it buys us some really nice theoretical properties, because we have a category that is fibered over finite distributive lattices, which is finitely complete and is a very nice category that we really understand. And so if we wanted to take limits in this category, which we want to make sense of, like these high-level methods for constructing proofs in a future proof assistant, then there is a way we can do this, which is to take a diagram in this over category, go downstairs, take the limit downstairs, and now we have an object that we can try to pull this diagram into a specific fiber, and then this specific fiber over the limit object downstairs is just going to be a functor category, and so we know how to take limits there. And since it's functors into C and we're trying to take limits there, that is where we're going to recurse into taking limits in C. So if it's an n-fold iterate of this construction, this is going to give us a way to reduce down to the limits in the original category labels. Okay, so there's a theorem that if C has geolimits, that ln C has geolimits, and crucially, what happens is that our Posetal diagrams, being objects that satisfy this technical condition, which looks a bit annoying to check, we don't actually have to check it in practice if we're getting new Posetal diagrams out of finite limits or vault ones, because this subcategory is closed under finite limits, which is a really, really strong form of invariant maintenance. Right, we can construct really complex diagrams out of smaller ones without ever checking this invariant. So at the end of the talk, I will go through what we covered. Here again, we introduced this notion of Posetal string diagrams, and we have a combinatorial encoding for them in terms of Birkhoff duality and this interval construction, which are our combinatorial gadgets for the day. We gave a recursive procedure for computing limits in this context, and these are powerful primitives that can form the basis of a future proof assistant that works with this structure. And our future work will focus on exploring the structure of these higher categories. All the details of this paper of this talk are in this paper, and thank you so much for listening.
Okay, let's thank Chiara.